To the earliest observers, the cosmos was the realm of the gods. They controlled day and night, the passage of the sun and moon. So too the constellations, and those wandering stars we know today as planets. Great monuments honoured the gods, but such monoliths had a practical function. They were the first observatories, marking the rising and setting of the sun, the moon and the stars, a celestial calendar with which the ancients could measure the seasons and predict events. Thus was born astronomy. Today, this nightly progress of the stars is little changed from the view of those first observers. What has changed is our understanding. Myth has yielded to science. We know, for instance, that the band of light in this time-lapse isn't milk spilt by the gods, but an edge-on perspective of our galaxy. It's the Milky Way, home to the sun and all the stars we see in the night sky. One galaxy among the 50 billion thought to comprise the universe. Face on, the Milky Way is a spiral of some 200 billion stars, many like our sun. They revolve around the galactic centre, at whose heart, most probably, is a massive black hole. Carrying Earth and the planets with it, the Sun takes 225 million years to complete one orbit of the galactic centre. Lying in a spiral arm, the Sun is 2/3 of the way out from the centre. Quite remote from the seething energy of the core, with its veil of gas and dust. Like the stars of our immediate neighbourhood, the Sun is yellow, average and middle-aged. And as astronomers discover more and more planets around other stars, the Sun is certainly not unique. This is our own backyard, the 9 planets of the solar system. Gas giants like Saturn and Jupiter, and 4 inner planets, rocky little worlds that include blue Earth. The spin of our tiny planet, an axis tilted by 23 degrees, and Earth's annual orbit of the Sun determine our view of the cosmos. That window changes night by night, season by season, latitude by latitude, all charted in this graphic guide to the heavens. Stars are grouped into patterns or constellations, often characterized in celestial mythology. With computer animations, familiar constellations, and pinpoint destinations, the night sky comes alive. Objects visible only in binoculars or telescopes, or best understood with graphics, are signposted by the nearest star or constellation line. As with all the planets of the solar system, Earth revolves around the Sun. Each orbit takes a year, shorter than Mars and the outer planets, longer than the 2 innermost. Imagine a line extending from Earth through the Sun to the background stars. During the year, as Earth orbits the Sun, so the stellar backdrop changes. We can't see the stars, of course, because the Sun's so bright. But if we could, this is the path the Sun would appear to take from May to September. Astronomers call the line the ecliptic. Looking in the opposite direction, in the evening this would be our view, a view that shifts from night to night. Season by season, the change is obvious. But over 24 hours, the shift is almost imperceptible. Because the stars rise and set just 4 minutes earlier each day. In 3 months, a shift of 6 hours. Again looking toward the Sun, remember it's our annual orbit of the Sun that causes its apparent journey along the ecliptic. The stars through which it passes are the constellations of the zodiac. The ancients saw them as heavenly figures: Taurus the bull, Gemini the twins, Cancer the crab, and Leo the lion. Later in the year, after Leo, Virgo the virgin. Then Libra, the balance or scales, and Scorpius, the scorpion. Ophiuchus, the serpent-bearer, is ignored by astrologers, adding an extra constellation to the 12 used in horoscopes. Next, Sagittarius, the archer, Capricornus, the sea-goat, and Aquarius, the water-bearer. In the 4th and final season, Pisces, the fishes, Aries, the ram, and Taurus, the bull, where we started this cycle. The 12 signs of the zodiac used by astrologers have little in common with the 13 zodiacal constellations of modern astronomy. Astronomy is science. Astrology is not. The 8 innermost planets of the solar system orbit the Sun in roughly the same plane. The exception is the 9th, distant Pluto, with its eccentric orbit. This common plane means the innermost planets we see always appear on or close to the ecliptic, and they move quite differently through the sky to the stars. The workings of the solar system explain why planets don't feature in the star maps of this graphic guide. With their slightly elliptical orbits, the planets circle the Sun at different speeds. Jupiter, the outermost here, takes 12 years for an orbit. The innermost, Mercury, just 88 days. Venus and tiny Mercury are best observed shortly after sunset and just before dawn. Neither climbs far above the horizon, so tight are their orbits of the Sun. Mercury is difficult to see, barely clearing the skyline. But Venus, the most brilliant planet, can be bright enough to shine in daylight. Venus and Mercury lie between the Sun and Earth with its circling moon. The planets farther out, like Mars, Jupiter and Saturn, display the weirdest movements in the heavens, so-called retrograde motion. Once a year in the zodiac, the planet Jupiter hiccups in its normal west to east motion, with a little backward loop. The same happens with Saturn, here through 2 consecutive years. With Jupiter the example, the cause is the faster solar orbit of Earth. As it overtakes Jupiter, the planet appears to go backward. Then, as Earth swings toward the other side of the Sun, Jupiter goes forward again. The Moon. After the Sun, the brightest object in the sky. Both a fascinating partner and the curse of astronomers, denied the dark skies essential for the best observing. The Moon, our mysterious neighbour. Mysterious because the ancients must have puzzled at its monthly phases. The Moon has no light of its own. It merely reflects the sunlight, constantly illuminating half its face. In the 27.3 days of the lunar orbit, the amount of lit surface we see from Earth changes day by day, like this. The Moon isn't in the star maps of this graphic guide. As with those wandering stars, the planets, the Moon has a different dance to the stars of the cosmos. It's because we have the moon that we enjoy the greatest astronomical spectacular, a total eclipse of the sun. There'd be more if it weren't for the 5-degree tilt of the moon's orbit with respect to the plane of the ecliptic, here in green. During each orbit of Earth, the moon twice intersects the ecliptic plane, here and here. For an eclipse to occur, Earth, Moon and Sun must all be in line at an intersection. Imagine you, the viewer, are the Sun. As alignment approaches, here's the total eclipse. If the intersection is on the far side of Earth, the event is a lunar eclipse. A lunar eclipse works like this. Moving into the shadow of Earth, the moon turns blood red. Indirect light from the sun is bent and filtered by Earth's atmosphere and projected onto the moon. Lasting up to 1 hour and 3/4, a lunar eclipse is always seen on the night side of Earth. Now an eclipse of the sun, but because the moon's orbit is slightly elliptical, this eclipse isn't total. The moon's shadow doesn't quite reach us. The result is an annular eclipse. The moon, at its farthest from Earth, is too distant to fully obscure the sun. This time, the moon is closer in its orbit, close enough for the dark inner shadow, the umbra, to sweep Earth at supersonic speed. Such an alignment happens about 70 times a century. On Earth, the umbra is creating a total eclipse. The outer penumbra delivers a partial. For those in the shadow of the umbra, and with a clear sky, totality verges on the magical. As the moon creeps over the brilliant solar disk, this partial phase can last 1 hour and a half. The diamond ring. The moon is shutting off the sun. Then, as the last beams twinkle through the lunar mountains, Baily's beads. And totality. It happens because the sun is 400 times larger than the moon, while the moon is 400 times closer to us than is the sun. Beyond the sun, the moon and the planets are the stars of this graphic guide. Stars that each night appear to journey through the heavens. But it's not the stars that are moving, it's our planet, a daily rotation on an axis hitched to the celestial poles. The pole star, Polaris, marks the north celestial pole. Around it, star trails reveal the rotation of planet Earth in this overnight exposure. The south celestial pole has no marker star, just the nearby constellation of Crux Australis, the Southern Cross. As Earth rotates, so the sky appears to circle the emptiness of the south celestial pole. We see the varying brightness of stars, and 2 blue patches, neighbouring galaxies to our Milky Way. Here's how to find the North Celestial Pole. Identify the Plough or Big Dipper, an easy pattern. It's part of Ursa Major, the constellation of the Great Bear. 2 stars point the way to the pole star Polaris. We've reached the North Celestial Pole. Our view is north from the mid-latitudes of the Northern Hemisphere. It's mid-evening. With Ursa Major, these are the circumpolar constellations, stars that circle the pole. From this latitude, they don't rise and set like most constellations. But they have their seasonal shifts. 4 minutes a night, 6 hours every 3 months. For the south celestial pole, string a line from Crux Australis, the Southern Cross, to Achernar, a brilliant star. The midpoint is the pole. A whole gaggle makes up the circumpolar constellations. Our view is south from the mid-latitudes of the Southern Hemisphere. It's mid-evening. These circumpolar stars don't rise or set, but they conduct their seasonal circuit. For the observer, whatever the season, only half the sky is visible from any point on Earth. In the Northern Hemisphere, this is the view from the mid-latitudes, the first zone featured in each of our 4 seasonal guides. Next is the equatorial zone, the tropics, the second featured in our guides. The third is the view from the mid-latitudes of the Southern Hemisphere, from places like Australia and southern South America. We're in the Northern Hemisphere, looking at the northern sky. Our target is the pole star, Polaris. Viewed first at 40 degrees north, say from Washington, D.C., Polaris drops lower in the sky, the farther south we travel. At Panama City, just 10 degrees north of the equator, Polaris would be here. South of the equator, Polaris is gone. Instead, in this view to the south, we see the South Celestial Pole. The farther south we go, the higher the pole rises. Now, at about 40 degrees south, this is the view from Melbourne, Australia. Although the tilt of Earth is always 23 degrees, its axis hasn't always pointed to the celestial poles of today. It's because Earth wobbles like a spinning top. Known as precession, the main cause is the Moon's pull on the equator. The effect on the North Celestial Pole is to move it around a great circle. Once the North Star was Thuban. Today it's Polaris, and in 4,000 years' time, it'll be Alderamin. The whole cycle takes just under 26,000 years. As with maps of the world, astronomers divide the sky into a grid. Here, the celestial equator is drawn directly above Earth's equator. To the north, at 10-degree intervals, are lines of declination. It's the same to the south. They're like latitude lines. This line equals 0 longitude. It's called the first point of Aries. To the left, divided into hours, minutes and seconds, are lines of right ascension east, and the other side, lines of right ascension west. A reference grid that can pinpoint any celestial object. And there's a handy way to do it. The outstretched hand at arm's length measures off 15 degrees of sky, an hour's right ascension. The clenched fist is 10 degrees, again held at arm's length. The span of 3 fingers, close together, is 5 degrees. And finally, the little finger, set at arm's length against the heavens, is just 1 degree. But that's bigger than you think. In lunar terms, it's a lot of sky. By night, the moon may appear the largest celestial object, but it measures only half a little finger, half a degree. To get the best from stargazing, the observer needs a telescope, or at least good binoculars. Too much is missed by naked eye. For the new observer, better to buy binoculars with quality optics than a poor telescope. The investment will last a lifetime. Marked on every pair are numbers specifying magnification and lens size. These 10 by 50. The 10 indicates that this pair will give a 10-fold magnification of the image. The 50 is the size of the lenses, both 50 millimeters. Here, the eyepieces are marked 5 millimeters. That's the width of the exit pupil, the light beam from the eyepieces. The size you need depends on age. If you're under 40, the pupils of your eyes will dilate to 7 millimeters. If you're over 40, just 5. If you're young, you'll see best through an exit pupil of 7 millimeters, so use binoculars marked 7 by 50 or 10 by 70. Dividing the numbers gives the exit pupil. Compared with binoculars, telescopes are expensive. They must be solidly mounted on the likes of a rigid tripod. There are two sorts of telescope. This is a refractor. Light is collected by a lens and focused in the eyepiece. The minimum useful aperture is 75 millimeters. Telescopes with apertures greater than 100 millimeters are usually reflectors. Popular sizes are 150 and 220 millimeters. Light is collected by a primary mirror on the right, bounced to a secondary mirror, and diverted to an eyepiece at the side. The detail and color we see in an astronomical object depend on how we gather its light. The bigger the lens or mirror, the more light is concentrated on the retina. But the naked eye is poor at seeing color at night. Unaided, this is how we see the Orion Nebula, lower frame. It's still black and white through binoculars or a small telescope. A moderate telescope gives more detail, but only through the biggest instrument does Orion's glory emerge, and that coaxed by supersensitive imaging. Many of the images in this graphic guide come from powerful professional telescopes, like this one in the Andes. Or from here in Australia, where astronomer David Malin combines long-exposure photography with special processing techniques. He reveals the true colours of stars. In this case, the true colours and detail of his Orion Nebula. Huge instruments, like the Very Large Telescope in Chile, gather light as few stargazers can. Synchronized and combined with 3 others, this mirror equals a 16-meter eye. By comparison, orbiting 600 kilometers above, the Hubble Space Telescope has a modest mirror. But out here, it's untroubled by Earth's atmosphere. Hubble's brilliant pictures feature throughout this graphic guide. From our vantage point on Earth, and from above it, we've learnt how to view the cosmos. But how do we measure its distance? Starting locally, our tiny planet is a mere speck against the Sun. The Sun has more than 100 times the diameter of the Earth. This local star of ours could swallow us 1,000,000 times over and still have room to spare. And here's another measure. Light from the Sun takes under 8.5 minutes to reach Earth. And there's the clue. Using the speed of light, 300,000 kilometers a second, astronomers measure distance. To the nearest star system, Alpha Centauri, it's 4.3 light-years. In other words, it takes more than 4 years for the light from Alpha Centauri to reach us. In terms of the Milky Way, from the Sun to our galactic center is 30,000 light-years. Finally, a preview of some objects we'll meet in the seasonal sky guides that follow. The spiral arms of this galaxy abound in nebulae. We're interested in the pinkish ones, clouds of glowing hydrogen gas. Like the Lagoon Nebula in the Milky Way, such clouds are starbirth regions known as gaseous emission nebulae. Another example is the Rosette Nebula. Emission means that the nebula emits its own light. The rosette surrounds a group of stars called an open cluster. An open cluster may be a few dozen stars, or hundreds scattered across 50 light-years. The most famous open cluster is the Pleiades, or Pleiades. These are reflection nebulae, clouds of gas and dust reflecting coloured starlight. 2 more, beautifully reflecting light from embedded stars. Now to dark nebulae, not holes in space, but dense clouds of dust. On the left, the Cone Nebula, a classic dark nebula in brilliant surroundings. And here, the most famous dark nebula, the Horsehead. Next, planetary nebulae. This is the Helix Nebula, formed as a dying star expels shells of gas. Another, more complex, is the Cat's Eye Nebula. And even more complex, the Hourglass Nebula. A planetary nebula is a form of emission nebula. So too is a supernova remnant, here the Crab Nebula. Supernova remnants are the entrails of giant stars that have exploded. As with all emission nebulae, supernova remnants generate their own light. Like tiny outriders around the great disk of our galaxy, float some 150 globular clusters. They're bunches of ancient stars, some tightly packed with dense cores. Others looser. They may contain tens, even hundreds of thousands of stars. There could be 1 million in one of the largest globular clusters, 47 Tucani. Lastly, to galaxies. The blue patches in this time-lapse are the Magellanic Clouds, 2 satellite galaxies of the Milky Way. With no distinctive shape, they're called irregular galaxies. By contrast, Andromeda is a well-defined spiral galaxy and largest member of our local group. Beyond that group, an elliptical galaxy with a dusty band, known as NGC 5128. Still farther, this one is an edge-on spiral, its reference, NGC 4945. And another, NGC 4565. NGC means New General Catalogue. Even deeper into space, the Sombrero Galaxy is also an edge-on spiral. Here's an elliptical galaxy, M87. M is for Messier, the catalogue of a French astronomer. This is a face-on spiral, NGC 2997, 55 million light-years from home. And this, a barred spiral, NGC 1365, at 60 million light-years. The central bar also features in NGC 1300, at 75 million light-years. Most galaxies occur in groups, some with just 2 or 3 members. Others are vast, like the Virgo cluster, bustling with some 3,000 galaxies. A little more distant is the Fornax cluster, less rich in galaxies, but sporting some gems. Still farther, the Coma cluster, with more than 1,000 galaxies. And here, the distant Perseus cluster, a rich but faint array. These are the most remote galaxies ever glimpsed, 4 billion times fainter than stars we see by naked eye. Images from the Hubble Space Telescope. No matter we'll never glimpse them, for the cosmos is an endless journey of fascination, however we view it.